Breaking physics, gold superheated 14x beyond melting point. Prepare to be amazed as we delve into a mind-boggling scientific discovery. Breaking the limits, superheating gold beyond belief. Scientists have achieved the seemingly impossible by superheating solid gold to an astonishing 14 times its melting point, defying a theoretical barrier known as the entropy catastrophe. But here's the twist: this groundbreaking experiment opens up a world of possibilities and challenges our understanding of phase transitions. Entropy, a fundamental concept in physics, governs the universe's tendency towards disorder. It's like a universal rule that everything must follow, and it's a big deal. Simply put, entropy measures how chaotic a system is. Think of a solid ice cube compared to liquid water. The water molecules are all over the place, giving it higher entropy. Now, here's where it gets interesting. While solids generally have lower entropy than liquids, there are extreme cases where this rule can be bent. Scientists have theorized that liquids can be supercooled below their freezing point, reaching the same entropy as a solid. Similarly, solids can be superheated to temperatures higher than their melting point, matching the entropy of their liquid counterparts. This brings us to the entropy catastrophe, a critical temperature where a superheated solid and a liquid have the same entropy. For gold, with a melting point of 1064 degrees Celsius, this temperature is around 3 times that. But reaching this threshold isn't just a walk in the park, it's a complex dance with physics. Enter Thomas White and his team from the University of Nevada, Reno. They tackled this challenge by using incredibly thin gold films, just 50 nanometers thick, that's smaller than a virus. With a powerful X-ray laser, they heated the gold for a mere 45 femtoseconds, a millionth of a billionth of a second. In this blink-and-you'll-miss-it moment, the temperature of the gold sample skyrocketed. Metals are like a sea of electrons surrounding positive ions. The electrons on the outer shells are loosely bound, giving metals their unique properties like conductivity and shine. When the laser hit the gold, it excited these outer electrons, spreading energy throughout the sample. Within a fraction of a second, every atom was vibrating with this increased temperature, and the researchers measured this motion. The team used 2 different methods to heat the gold film, and in both cases, they surpassed the entropy catastrophe temperature for over 2 picoseconds, 2 trillionths of a second. The key to bypassing this threshold: heating the sample extremely quickly, creating a rapid electron and atomic motion, but on such a short timescale that the sample didn't have time to expand. This rapid heating might be the secret to maintaining a crystalline solid structure. But here's a caveat: temperature is linked to the average particle motion at equilibrium. In this experiment, the system was pushed out of equilibrium by the laser heating, so the shaking of the atoms might not represent a true temperature measurement. Nonetheless, this experiment takes us to the very edge of phase transition physics, leaving us with a tantalizing question: what could we achieve if we mastered the control of superheating and melting materials? This groundbreaking study, published in the journal Nature, opens up a world of possibilities and challenges our understanding of the fundamental nature of matter. So, what do you think? Are we on the cusp of a new era of material science? Let's discuss in the comments and explore the potential implications of this fascinating research. Shocking discovery: scientists blow up gold with lasers, shatter physics model. Imagine gold being blasted apart with the world's most powerful lasers, and the results unexpectedly appending what scientists thought they knew about the limits of physics. That's exactly what happened at the SLAC National Accelerator Laboratory, where researchers catapulted gold to an astonishing 14 times its normal boiling point, only to realize that their findings shattered a long-standing and widely accepted scientific model. But here's where things get really interesting: they didn't just challenge the model, they may have rewritten an essential chapter in our understanding of matter itself. In an eye-opening study published in Nature, a team of physicists unveiled a brand new way to directly measure the temperature of matter under extreme conditions. Think pressures and temperatures so fierce they resemble the core of a star or the sizzling interior of a fusion reactor. Their method involved 2 daring experimental steps. First, they used an immensely powerful laser to superheat a chunk of gold so that it resisted expanding, even as it endured temperatures far beyond what any precious metal is expected to handle. Then, using intense bursts of X-rays, they measured how these beams scattered off the gold, calculating minuscule changes in the X-ray frequencies. This allowed them to precisely determine the speed and temperature of the gold atoms in real time. Here's the part most people miss: the previous consensus in physics maintained that no material, especially metals like gold, could be heated more than 3 times its boiling point, roughly 1948 degrees Fahrenheit, or 1064 degrees Celsius in gold's case. If you tried to push it any further, the theory said, you'd hit an entropy catastrophe, the point at which superheated matter essentially blows itself apart and can't exist in any meaningful, measurable way. But in this experiment, the scientists took gold to a jaw-dropping 33,740 degrees Fahrenheit, 18,726 degrees Celsius, over 10 times past that accepted theoretical boundary. Dr. Thomas White, the study's lead author from the University of Nevada, put it candidly, we were looking at the data and thinking, is this axis right? That can't be, the material is way hotter than we thought possible. It's worth noting this scorching state lasted only for a handful of trillionths of a second, and then, as expected, the gold erupted. But even that blink of time was long enough for their new technology to get a direct reading on the temperature, a feat never achieved in such extremes before. White couldn't help but marvel at his unusual job. I get to blow things up with giant lasers for science, and it teaches us completely new things. How cool is that? But this result opens a Pandora's box. Was the old theory simply wrong? Will further tests on gold and other metals back up these findings, or could they reveal something even stranger? Senior author Bob Nagler of SLAC explained that temperature, despite being the most basic property we measure about matter, is rarely measured directly. Traditional thermometers rely on observing how temperature changes something else, like mercury expanding in a tube. That limitation makes studying extreme states, like the blazing core of a star or the searing tip of a re-entering spacecraft, fiendishly difficult, if not impossible. And this is where much of physics hits a snag, Nagler said. You can try to recreate these environments in the lab, but they tend to explode before you can gather meaningful data. Plus, you need to know the actual temperature of the thing you're trying to mimic, or your results won't match real-world extremes. It's the classic chicken and egg problem in science. To measure what you're studying, you first need to know it, but to know it, you need to measure it. This breakthrough, the researchers say, could finally give scientists a direct thermometer for the wildest, hottest, densest matter in the universe, a tool vital to everything from nuclear fusion energy research to understanding cosmic phenomena. For example, at the National Ignition Facility, scientists already blast laser light at gold cylinders to produce X-rays that help spark fusion reactions. But now, for the first time, they could measure the actual temperatures inside these critical components, clearing up long-standing uncertainties in physics that have persisted for decades. White and his colleagues are now expanding their work to other metals such as silver and iron, and early results seem promising. As they analyze this new data over the coming months, the entire project is gaining momentum, and perhaps inviting fresh controversy along the way. If gold and maybe other metals really have no superheating limit, what does that mean for our understanding of entropy and the fundamental laws that govern matter? Should the scientific community reconsider the very basics of how metals behave under extreme conditions, or do you think there's a yet-to-be-discovered piece of the puzzle everyone's missing? Would you trust this kind of revolutionary laser experiment, or stick to the tried-and-true theories that have guided science for years? Join the debate below. Your opinion could help shape the next chapter in modern physics. Gold superheating. Can it really heat 14 times its melting point? Imagine a material that can withstand temperatures far beyond its melting point, seemingly defying the fundamental laws of physics. This may sound like science fiction, but it's a reality that has left scientists stunned. Researchers have discovered that gold, when heated to an astonishing 14 times its melting point, remains solid, challenging our current understanding of superheating. But here's where it gets fascinating. This phenomenon has sparked a debate about the very limits of thermodynamics, and whether some solids may have no upper melting point at all. Superheating, a common occurrence where a solid or liquid can be heated beyond its melting or boiling point without changing state, has long been a subject of interest in the scientific community. For instance, a cup of water heated in a microwave can reach temperatures above 100 degrees Celsius (212 degrees Fahrenheit) without boiling, as long as the cup remains still and smooth. However, the moment the cup is disturbed, the water will violently boil, illustrating the delicate balance between thermodynamic states. For solids, many physicists have proposed an upper limit for superheating, known as the entropy catastrophe, which occurs at a temperature around 3 times the standard melting point in Kelvin. At this point, the entropy, or disorder, of the solid state would surpass that of the liquid state, potentially violating the second law of thermodynamics. This law states that entropy cannot decrease over time for most systems, making it a fundamental principle of thermodynamics. Now, a team of researchers led by Thomas White at the University of Nevada, Reno, has pushed the boundaries of superheating by heating a wafer-thin sheet of gold to 14 times its melting point, far beyond the predicted entropy catastrophe point. By using a powerful laser to heat the gold for an incredibly short duration of 45 quadrillionths of a second, and then measuring its temperature using reflected X-rays, the team made a groundbreaking discovery. We measured these temperatures, and we were like, wow, that's really hot. Like, can it really be that hot before it melts, says White, highlighting the astonishment and curiosity that drove their research. After verifying the accuracy of their measurements, White and his team re-examined the theory and realized that the rapid heating of the gold allowed its entropy to remain lower than that of the potential liquid state, enabling it to surpass the predicted temperature limit. It's essential to note, as White emphasizes, that this discovery does not violate the second law of thermodynamics. Instead, it challenges our understanding of the limits of superheating and raises questions about the true boundaries of thermodynamic states. The true limit of superheating remains an open question, leaving scientists to ponder, how hot can you make something before it melts? This inquiry has significant implications for our understanding of materials under extreme conditions, such as those found in planetary cores. Measuring the temperature of solids using this X-ray technique could provide valuable insights into the behavior of materials under intense heat and pressure on extremely short timescales, according to Sam Vinko at the University of Oxford. We don't really have a good thermometer for solids that you can look at on really short timescales, he notes, highlighting the potential applications of this research. The question of whether this phenomenon applies to other solids, aside from gold, and whether there is an upper limit to heating before melting, is a topic of great interest. As Vinko suggests, the thing that's intriguing here is to ask the question of whether or not it's possible to beat virtually all of thermodynamics, just by being quick enough so that thermodynamics doesn't really apply in the sense that you might think about it. This provocative idea invites us to reconsider the fundamental principles of thermodynamics and their limitations. But here's where it gets controversial. If some solids can indeed withstand temperatures far beyond their melting points, what does this mean for our understanding of the physical world? Does this challenge the long-held notion that thermodynamics is an absolute law, or does it simply highlight the complexities and nuances of thermal dynamics? We'd love to hear your thoughts. Do you think it's possible to push the boundaries of thermodynamics, or are there fundamental limits that cannot be exceeded? Share your opinions and let's spark a discussion about the fascinating world of superheating and thermodynamics.